All right, so when you are graphing exponential functions, some of you may have done some of this graphing before, or you may have talked about different models in science classes, like if you're taking biology or if you took it last year. So we're going to talk about how to graph growth and decay functions. We're going to do a review of domain and range, and then this is a new word. We're going to learn about asymptotes, and they are only going to be there with exponential functions. I know, it's kind of funny. Right, so for exponential functions, there is a standard equation. We're going to put that here. So the most basic one would be if you had y equals b to the x power. Okay, and this value of b is the base, and then your variable is your exponent. Okay, so what do the variables in the equation represent? So your b is your base. Okay, the exponent is always going to be the variable. Okay, so the variable is always in your exponent. A lot of times it will be x, but as we do some applications, like we're going to do those tomorrow, you're going to see that you can have different variables, like t is a common one. Okay, the other model, which is one we're going to be using more frequently, is a times b to the x. So b is still the base, x is still the exponent, but this value of a is the initial value. Okay, it is also the y-intercept. Okay, so a is the initial value, and it's the y-intercept. And that's for if you have like b to the x. There are some cases where you have different exponents, okay, and that can change. But we'll talk about those as well. All right, so types of situations, exponential functions will model. So can you guys remember examples from maybe some of your science classes where you talked about things that grow exponentially or decay? Mm-hmm. Yeah, so population growth is a big one. Any other types of growth you can think of? You guys ever talk about like bacteria multiplying? Yeah, no one? Yeah, and stock actually could be growth or decay. Okay, so stock values. We're doing the word problems together, but yes, we are doing lots of applications. So sometimes they might say like something doubles or triples. If that happens, then it's one of the very basic models. So if something doubles, you could just do 2 to the power of x. If something triples, it would be 3 to the power of x. So you could always model it that way. What about decay? Do you guys talk about any like decaying of masses in chemistry or biology? What about half-life? Do you guys do the half-life of different elements yet? Maybe?
No. I'm not going to lie. I don't know what a half-life.
So there's lots of different applications of the decay. So with the decay of mass, there's actually formulas to, if you've ever watched a crime show and they're like, oh, what do you put the time of death as? You can actually find that using an exponential function. You can also find like how fast something is decaying using exponential functions. You can also find the half-life. So there's a technique called carbon dating, where you can use the amount of carbon in an artifact to determine, to estimate really, when it was used.
What about like a dead deer on the side of the road? Figure out how long ago it died.
Yeah, you could if you knew what the body temperature was and the temperature outside. You could use Newton's law of cooling. Okay, so we are going to be graphing functions today. We're going to start with a very basic function, which is y equals 2 to the x. It is the doubling function, and then we're going to identify the domain and the range. Now, we've talked a lot about the domain this year, so we should know the domain is the set of x values. When we're determining the domain, do you guys remember what we're looking out for? I know, but what are the restrictions? Do you have situations? If you have a radical, you can't take the even root of what kinds of numbers? Negative numbers. Yep. What's the other situation? Fractions. Okay? Those are the only two situations we have right now. So if there is no fraction or there's no radical on this x, okay, then your domain is just going to be what? All real numbers. Okay? And for the range, we're going to be looking at the graph. So for every graph we make, we're going to be making a table of values. We are going to be using our graphing calculator, but with this one, we really don't need to. Let's review some of our exponential rules. Okay, so if you have 2 to the power of negative 2, how do you make a negative exponent into a positive one? Yeah, put it over 1. And then this becomes 2 squared. So this is going to be 1/4. So 2 to the negative 1 is going to be 1 over 2. What's anything to the 0 power? 1. Good. And then 2 to the first is 2. 2 to the second, 4. 2 to the third, 8. If we did 2 to the fourth, it would be 16. And we'll scale this 1 by 1 so we can graph these. Okay, so we're going to start with the 3. So at 1, 2, 3, we're up to 8. Okay, at 2, I'm at 4. So see, I'm just putting small dots on there. At 1, I'm at 2. At 0, I'm at 1. Here I'm at 1/2, and then 1/4. Okay, and then you can see it makes a soft curve there. Yep, and so I like to do this with the pencil, and I like to curve it like this. Okay, and then this is going to curve through these points here. Okay, and we're going to graph it on our graphing calculator so you can see what that looks like. So we have 2 to the power of x. I'm just going to set my standard window. Okay, now if you have like one of the newer flat calculators, you can see this blue line keeps going and going. Okay, with some of the larger calculators, the technology, the pixels just can't get small enough, so it looks like it stops, but it doesn't stop because you can keep plugging in negative numbers, right? If you have the negative 3, this would be 1/8, and they would keep getting smaller and smaller and smaller. Okay, so your domain, like we said, is going to be all real numbers because there's no restrictions. And that's going to happen a lot. So for the domain, so for your domain, I'm going to let you write the real number symbol, which is just the R with the line through it. So like I said, that's going to happen many, many times. Okay, now with the range, we're going to look at our table. So if you're looking at your table here, okay, I'm I'm at -8. That's where mine started because of what I did last time. But you can just scroll. Do you see how as the lower I get, you start seeing these E values? What do those mean? Yeah, those are scientific notation. So if it's e to the -4th, okay, you're going to have 3 zeros in front of this number. So they're getting really, really small. They're getting really, really close to 0. Okay, and here they're going to be growing exponentially. So they're going to get really, really close to 0. They are never going to touch 0. So for the range, we're going to say all values of y such that y is greater than 0. So not greater than equal to, it's just going to be greater than. Okay, and the reason why it's never going to reach 0 is there is something, this is called a horizontal asymptote. Okay, so the asymptote is a line a graph approaches the graph approaches. So approaches means it gets very, very close to, as the value of x gets very large or very small. So the smaller the x value gets, the closer this gets to the number 0. And this is a horizontal asymptote. And in exponential functions, the graph is never going to cross this line. Okay? Eventually, you'll learn about different types of graphs that have other types of asymptotes. There's vertical asymptotes and there are slant asymptotes. So the asymptote is represented by a dashed line. Looks like this. Also, should I zoom in? Is that too small? Sorry. I asked my last class, but I don't have people sitting there. Okay, and then it says, what is the horizontal asymptote for, it says the parent function. That's because y equals 2 to the x is a parent function of a function family. And we're going to label it above. Now, when we label those, you can use a marker or a highlighter. I think it's easiest to see with a highlighter. So because all of those values we saw in the table were approaching 0, this is going to get closer and closer to 0. So you'll mark it with a dashed line. Okay, and then you'll get y equals 0 in there. It's just hard to see on the line with the axis if it's y equals 0. If it's anywhere else, it doesn't matter. It's just if it's y equals 0, it can be kind of difficult to see.
Where's the put those arrows on the line?
Yep, so it is a line, so it is going to extend to infinity. And I do want the arrows on these as well if you haven't put them there. Okay, so the two types of exponential functions we have are exponential growth and exponential decay. Now, they have the same equation. So f of x equals a times b to the x. Okay, it's the same exact equation for both. The only thing that changes is going to be the value of b. So this is f of x equals a times b to the x, where the b value is greater than 1. So if it is exponential growth, the value of b has to be greater than 1. Okay, and if it's decay, the value of b is between 0 and 1. So it has to be greater than 0, but less than 1. And again, it does not include it. So if the base was 0, okay, this wouldn't even exist anymore. If the value was 1, do you guys know what 1 to any power is? Yes. So if you did 1 to the 9th, 1. If you did 1 to the negative 22nd, 1. Okay, so if you got 1 for every single answer, what kind of line would that be? Be a horizontal line, right? Just keep hitting 1 the whole time. Okay, so that would not be exponential. Now, here's a part that sometimes takes a little bit to wrap our heads around. A lot of times people associate growth with positive and decay with negative, but that is not true. So you can have growth in the positive direction. Let's actually we're just going to draw some rough sketches. So let's make our axes. Okay, so you can have growth in the positive direction. That's often the population is growing. Okay, and then earlier we talked about stock values, right? So it can grow in the positive direction, but it can also grow in the negative direction, right? Think of our national debt. That's growing in the negative direction, right? So you can have growth that's positive or negative. Okay, for decay, it's the same way. So when something decays, you can either start at a positive value